My Leetcode skills so clean, I'm like an artist. This is minimum amount of time to collect garbage. Let's go ahead and get right into it. So you're given a zero indexed array of strings garbage, where garbage I represents the assortment of garbage at the ith house. Garbage I consists only of the characters M, P, and G, representing one unit of metal, paper, and glass, respectively. Okay, so you have all these locations. I guess they're houses, right? And then there could be, multiple pieces of metal. There could be multiple pieces of paper. There could be multiple pieces of glass, right? There could be none. But there's, some assortment of these trash items, these unique trash items at each house. Now, if you want to pick up one unit of garbage, regardless of the type of garbage, it's going to take 1 minute, right? So if I have glass, and paper, it's going to take me 1 minute to collect the first piece of glass, another minute to collect the second piece of glass, a third minute to collect the remaining piece of paper. So 3 minutes in total. You are also given a zero index integer array travel, where travel I is the number of minutes needed to go from house I to house I plus 1. Okay, so there's like a row of houses, right? You're in, a suburban hellhole, and there's just all these houses, just these cookie cutter clone houses that boom, boom, boom in a row, right? If I start at house 0 and I want to get to house N, I'm going to have to go from house 0 to house 1, and house 1 to house 2, and house 2 to house 3, and house 3 to house 4, and so on and so forth, all the way till house N. So they're all in this line, right? There are 3 garbage trucks, right? We have 3 types of trash, 3 garbage trucks, kind of makes sense, in the city, each responsible for picking up one type of garbage. Each garbage truck starts at house 0 and must visit each house in order, right? So you can't you can't teleport, from house 0 to house N, right? In order to get from house 0 to house N, you have to go to all the other houses in between. It must visit each house in order. However, they do not need to visit every house, okay? The only one garbage truck may be used at any given time, so it's very inefficient. While one truck is driving to picking up garbage, the other 2 trucks cannot do anything. Return the minimum number of minutes needed to pick up all the garbage. Okay, so there's 2 ways that you incur cost, right, in this problem, right? The first way, so let's just say, how does time get increased? It's a terrible way of stating it. But there's 2 ways in which time can increase, right? Time can be increased while I am picking up garbage, right? In particular, it takes 1 minute per item that the truck is picking up, right? So that's one way that you incur costs, right? Because you have to literally pick up all the garbage, right? So when you're picking up all the garbage, you have to spend time doing that, right? So if there's 10 units of garbage, it's definitely going to take 10 seconds for this whole shebang to happen, right? The second way you incur cost is traveling from house X to house X plus 1, right? So when I travel from house X to house X plus 1, there's a certain travel cost associated with it. Now, the minimum solution here is what? Well, I guess you'll notice it if we look at the example. So let's look at the example, and then we'll tie back to this and notice what, the only real, very slight, subtle optimization we can make to this problem. If you want to call it an optimization, it's so simple it almost seems bastardly to use that terminology. But, this problem's a medium. I would say it's more so an easy, but whatever, it adds to your medium count, so it kind of is a beautiful problem, just for the fact that you could say you did another medium when really, it's more so an easy. Okay, so let's look at this example here, right? So we have garbage equals, I'm garbage, right? Garbage equals GP, GP, GG, travel equals 243. Well, you're going to have these 3 trucks, right? You're going to have this glass truck, this paper truck, and this metal truck. So the glass truck is going to start at this house, right? It's going to pick up this garbage, and we're going to incur 1 minute of time from doing that. But it's also going to need to travel to this house. So in order to do that, it's going to cost, okay, what is travel? So it's going to cost 2 minutes, right, to travel. Let's put some space in between these houses to signify that, it takes time to get here. So in order to travel from this house to this house, right, it's going to cost another +2. And then in order to travel from this house to this house, it's going to cost +4. And then he's going to pick up the garbage. They are going to pick up the garbage at this address. So that's going to cost 1, right? Because in order to pick up the garbage, it's going to cost 1 whatever. And then he's going to have to travel all the way to this house, which costs 3. And then he's going to have to pick up 1 from here and then another 1 from here. So that's the total cost occurred from using the glass garbage guy. All right. Next we have, so we'll call this garbage truck cost, I guess, GTC. Sounds cool. Then we have the paper truck, right? The paper truck starts here. So maybe I should move this guy over. He starts here, picks up nothing, but then he needs to go to the next location. Now he's here. So we'll call this paper truck cost. So he spends 2 here. Now he's at this location. He has to pick up this trash. So that's +1, right? And then he has to move to this location. So that's another +4. Now he's here. He has to pick up this paper, +1. Just notice that everything gets shifted over when you do that. Right? Okay, it's all no longer vertically aligned, but whatever. Right, so now that the paper truck is here, what you'll notice is, well, you know, I could continue to go down this path, right? And I would incur an additional cost of 3 to travel from this house to this house. But the optimization here is, well, I'm done here. Like, there's no more trash for me to pick up. So I don't need to keep going. Why keep going if the job is done? So I'm just going to stay here. And that point is even further exemplified when you look at the metal truck. Or when you look at the metal truck, it starts here, right? Well, there's no metal for this truck to pick up. Since there's no metal for this truck to pick up, there's no point for this metal truck to move at all and incur any cost. It can just stay right where it's at because there's no metal. So let's not increase the cost, right? So there's no additional cost that we incur from the metal truck because there's no metal for it to pick up, right? So since there's no metal for it to pick up, it doesn't have to go through the whole process. What would be problematic and kind of, it would still be the optimal solution, but it would be an annoying solution is imagine there was metal at the end, right? In this case, even though there's no metal here or here or here, since there's metal at the end, we're going to have to travel through the whole system because we can't teleport. So we'd have to go here and incur 2 and go here and incur 4 and go here and incur 3, right? But since we're in the case where, you know, there's no metal in the system, then we don't need to move it. So then our cost is just the sum of whatever this is, and it turns out the sum of this is 21. Now, I may have forgotten to count 1 or 2 things. I'm not genius, but let's just see. Maybe I got it right. So 4, 8, 9, 10, 13, 15, 16, 17, 18, 21. I think I overcounted 1 thing, but it doesn't matter. You get the gist of the problem here. So this is unavoidable, right? I guess the note here, right? Conclusion from this is like, if there's trash, you have to pick it up. So you're going to spend 1 minute of time picking up all the trash. So this is unavoidable. This is unavoidable because we have to pick up all the trash. Pick up all the trash, right? It's unavoidable issue. This, on the other hand, where, well, we don't need to travel. We don't need to travel to all houses, always. We only need to travel. So here's the key point here, all right? We only need to travel to the last house that has the item we pick up, right? So in this initial problem, you'll notice, right? The farthest P has to go is here because that's the last P in the system. There's no longer any more pieces of paper for it to pick up, so it'll stop there. But since it has to go in a row, it's going to have to go from house 0 all the way there, right? It's going to have to go all the way to this index, and then it can stop, right? The glass garbage cut, since there's glass at the last index, it's going to have to travel all the way to the last index, right? For M is going to have to travel nowhere because there's no M, so it doesn't have to travel at all, right? So we can minimize the travel cost by figuring out the farthest we need to go to pick up trash and going no further, okay? Right, so in this example, M would only have to travel here, right? Versus G and P would both have to travel here. So we'd have to spend 3, 6, 9, right? 3, 6, 9. 3, 6, 9, one more. No, 3, 6, 8, because we have to spend 8 to pick up all this stuff. But then, you know, we're going to spend 13 twice because we're going to spend 3 for P to get here and 10 for P to get here. And then 3 for M to get here and 10 for M. Start over. We have to spend 8 to pick up all this trash. We have to spend 3 for P to get here and 10 for P to get here. And then 3 for G to get here and 10 for G to get here. So that's 8 plus 13 plus 13, 26. Wait. 13 plus 13 is 26 plus 8 is not 37. So what am I doing wrong here? Okay. Takes 7 minutes. Oh, there's metal here. My bad. So M has to stop here. G and P has to stop here. Dude, who knows? Who knew those would be so hard? So there's 8 items we have to pick up. So let me just write this down. We have to pick up 8. M has to travel to 1. So that's going to cost 3 in traveling. But he doesn't have to travel any further versus GP have to travel all the way to the end of the system. So G has to spend plus 3 plus 10 in traveling. And then P has to spend plus 3 plus 10 in traveling. So that's 11 plus 13, 24, plus 13, 37. Who knew that would be so hard? Okay. So with that said, let's go ahead and get right into the problem. Okay, so all we really need to do, right, is find the last house of which we need to travel. And we can do that in reverse, right? So if we want to find the last instance of something, it's the first instance of something in reverse, right? Like if I wanted to find the last instance of A in this system, well, the last instance of A is here, right? But that's also the first instance of A if I was looking in reverse, right? If I was going in this direction, the last instance of A from the left is the first instance of A from the right, okay? So if we wanted to just find the farthest somebody would have to go, we just need to find the first instance of that item they need going in reverse, right? So we'll go ahead and do that now. Okay, so whoa. So at the end of the system, I'm trying to think about the order of which we're gonna do this. Let's just erase this. We don't need it. Okay. So we're gonna have a garbage index. So we'll find the last index of which garbage exists, and we'll go in reverse. Okay. We'll do this for each index. So we'll do for garbage. We'll do it for, maybe this isn't the cleanest way of doing this. We'll do it for garbage. We'll do it for metal. And we'll do it for paper. Why am I making this harder on myself? Okay. And then we'll just say, well, since we're going in reverse, we'll say, well, if G, right, is in garbage at G index, then we found the first occurrence of garbage. If we found the first occurrence of garbage from the right going in reverse, right? So we found the first instance of garbage coming from the right. That's technically the last instance of garbage coming from the left. So this would be the last house we'd have to travel to, right? So we would just break. Then we can play this game 3 times. So we'd say if M in M index break, if P in P index break. So we're saying if there's metal at this house, this is the first time that we're seeing it because we're going to break. So this would be the last house we have to travel to. Okay? So then our total cost is, well, we have to sum the length of each house in garbage, right? The amount of garbage in each house. Right? Because the length of this, right, is the number of items we have to pick up at this house. So I'm basically just saying all the items, we're going to have to pick them all up, and it's going to take 1 minute to pick them all up. And then what we're also going to have to do is incur the cost of picking up all the garbage, right? So we would say, I'm trying to think about this finesse, right? We take all the travel cost up into the garbage that we're picking up for each. We want to sum that. I'm going to do it 3 times, so this isn't technically like as efficient as it could be, but in terms of time complexity, it's the same. Okay. We'll just call it last house index. That's ugly. Last house index. We'll just call it index. You know, sometimes you play these games and then you end up calling it something that doesn't make any sense. Whatever. For index in G index. So I'll explain what this is going on here in a minute. And P index. So basically what I'm saying is, what's the total travel cost for each of the trucks, right? Because this is the last house that the glass truck has to travel to. This is the last house the metal truck has to travel to. This is the last house that the paper truck has to travel to. So I'm basically saying, what's the cost to travel to all those houses? And the sum of that will be the total cost that I incur to travel to each house. Now this might be wrong because there's like be a little one-off error here or something. Okay, it's fine. And then let's go ahead and submit that. And you just pray. Let's go, son. Come on, dog. Are you playing with me, dog? All right, so how does this work? Well, right. So just to summarize, all we can do to optimize this problem, right, is find out the last house we have to travel to. So to find the last house we travel to, we look at all the houses in reverse, and we find the first house of which has the trash that we need to pick up. So that would be the last house from the left, right? The first house from the right is the last house from the left. So we find that last house from the left for each of the garbage trucks. And then we just say, well, we're going to have to pick up all the garbage anyway. So whatever that total time is, we're going to spend that much time picking it up, right? If there's 10 items, we're going to spend 10 minutes picking it up. And then we just find how much it would cost in terms of travel time to travel to all those houses. Okay. And now this could probably be made shorter and I get a little shorter solution, but I don't really care that much. Okay. So what is the run and space complexity? So these two have proportional lengths. So let's just say that n is the length of garbage. Okay. Now this is going to take, at worst case, O of n time, right? Because if there is none of that trash available, it's going to go through the whole list. So we're going to go through the whole list 3 times, right? So that's O of n time. O of 3n time is O of n time. And then we're going to just sum this. So we're going to look at all the houses and all the houses links. So that's O of n time. And then we're just going to sum the travel list. It could be that all the items are in every house, so we have to go through the whole list 3 times. So then we sum travel 3 times, so it's 3n. So it's 3n, 3n, n, 4n, 7n. 7n is proportional to O of n. Okay. So for time, it's O of n. And then for space, well, you know, we just create these 3 variables, right? We create these 3 variables independent of how many houses there are, right? At the size of n, We just create these 3 variables and we use these 3 variables to sum some value. So that is technically O of 1. Okay, guys, this problem wasn't really like based on any data structure and algorithm. This would honestly be a pretty good problem to give someone in an interview if you expected that they were maybe good developers, but they weren't that well versed in data structures and algorithms. I guess the closest thing you could relate this to is a greedy approach, right? A greedy approach meaning, well, the best solution is just to greedily pick the least number of houses, right? And to do that, you just pick, you just find the last house you would need to travel to in order to pick up what you need. You don't need to go any further. It's pretty intuitive. Okay. Peace out.